So what is important if we talk about ultra-fast lasers? So important is for sure it's the dispersion. So you can see here the dispersion, the refractive index of your silica, which is shown over the wavelength range, and you see that it changes about the 4 different wavelengths. So for femtosecond lasers, it's important to think about group velocity dispersion, so-called dispersion values. That means that different components travel at different speeds. And this in the end leads to a so-called chirp. And if we talk about a positive chirp, the red part of the pulse is always in front of the blue part. And the opposite, if we talk about a negative chirp, typically the blue part is ahead of the red part. And in normal materials like fused silica, the dispersion is positive up to 1.3 micrometer. That means in normal glass, red always travels faster than blue. So if we now talk about ultrafast fiber lasers in comparison to other technologies like solid-state lasers, there are some commercial advantages, like we have very compact lasers, they are maintenance-free, they are very easy to use, very cost-effective, have a high customer value and a low total cost of ownership. Some technical advantages are they are turnkey, they offer higher stability, they are very robust, offering a very low noise, we can get up to high-end laser parameters, and we typically have a scalable technology. So if we think about the physical answer why we talk about femtosecond fiber lasers, the simple answer is the light can guide in optical fibers, which makes your life much easier. So if you have 2 different refractive index, the light is propagating in the core of the fiber, as you can see on the right side. That means if you have a fiber, you can put also several meters in a box, which makes the lasers, as I said, very, very small. And physical effects are more present. So that means that all amounts are increased. So on the right side, you see a picture of a coil fiber, and you also see the nonlinear effects, which we'll discuss later. So you see the different colors within the fiber. And also for us, it's an amazing technology, and we can make benefit of a lot of physical effects here. So if we talk about ultrafast laser fundamentals, we first have to talk about dispersion, which we've seen a few slides before. So we saw that the red part of the pulse is propagating in front of the blue part, which means in the end it stretches the pulse in time. So this results in a longer pulse duration, and therefore a reduced peak power. You can see here on the left side a calculation of the pulse, which showing a 30 femtosecond pulse and the corresponding optical spectrum below. So you see the very broadband spectrum corresponding to the very short time event. Is the pulse now propagating through 5 centimeters of BK7 glass? You see that the pulse duration gets longer, up to 100 femtoseconds. So that means also that the peak power is reduced by the same amount. So roughly 3.3 times. So very important to understand is that if we talk about a linear effect, that this only affects the temporal profile of the beam. So as we can see, the spectrum is unaffected and it stays exactly the same as before. Compared to this, if we talk about nonlinear effects, which is mainly cell-phase modulation, the nonlinear effect in general only affects the spectral domain. So that means if we have, on the left side, we show you a pulse with a Gaussian spectrum and a pulse duration of 140 femtoseconds. And if we now propagate through a fiber and we ignore the dispersion, that means the pulse duration will stay the same and we get an increase of the spectrum, which means we have a spectral broadening from 16 to 102 nanometers if we propagate to 1 meter of optical fiber, if we ignore the dispersion. But now we've seen that we have to ignore one of the effects. In the real world, it's a bit more complicated. So if you want to calculate what happens with the pulse or the spectrum, you have to use the so-called split-step Fourier method, which means that cell-phase modulation typically broadens the optical spectrum, and if you have a broadened spectrum, you have more wavelengths, so the pulse stretching in time, it's getting more prominent. And so both effects affect the pulse propagation. So that means if you want to use or to calculate the pulse propagation, you have to change between the temporal and the spectral domain. And this is done by Fourier transformation. And if you do it one step and the next step, you can calculate the temporal evolution, then doing a Fourier transformation, going to the spectrum, and then make a calculation of the spectral evolution. In the end, this means if we start with a 140 femtosecond pulse and propagate through 1 meter of fiber, we have both effects, linear and nonlinear effect. That means we broaden the pulse in time, and we also broaden the optical spectrum, as you can see here on the slide on the right side. We broaden the spectrum from 16 to 30 nanometers due to nonlinear effects. So, in general, if we talk about ultrafast laser systems, how does it work? Typically, we start with an oscillator. We're generating optical pulses by so-called mode locating. They typically have smaller bandwidths of a few nanometers up to a few 10 nanometers, and typically having a lower energy. So then we have a so-called amplifier where we just amplify the power or the energy. And finally, we have a compressor where we time compress the pulse, which means that we are compensating for the dispersion effects. So it just affects temporal behavior of the pulse. So how is this done typically, let's say in the conventional laser? In the conventional way, we talk about just pulse amplification. That means on the red side, on the red part, we start with a short pulse oscillator, and then the pulse is stretched in time by using a grating stretcher, which reduces the energy or the peak power. This gets then amplified, and you get an amplified pulse, which is stretched in time, and then we use a so-called compressor, like a grating compressor, to compensate for the dispersion effects, which ends up in a very short pulse and a high energy and high peak power pulse. So typically the CPA scheme is stretching, amplifying, and compression. It has to be mentioned that in this scheme we avoid nonlinear effects, and therefore we avoid the spectral broadening, as we have seen that spectral broadening is done by nonlinear effects. So it's worth to mention that there was a Nobel Prize in 2018 for the scheme of amplifying optical pulses, but there's also disadvantages. So as we do not affect the spectral bandwidth, this is limited to the spectral bandwidth of the seed oscillator, and therefore the complete scheme is also limited in pulse duration, which means you cannot get a really short pulse duration.